What's up, guys? Happy Halloween. We're about to do a very quick problem showing you that the momentum operator in quantum mechanics is a Hermitian operator. All right, so on the page, what I have here is just a blank sheet. I'm going to write the word Hermitian operator. What is a Hermitian operator? It is an operator whose expectation value, so this is a general operator Q. A Hermitian operator has a real expectation value, which means its expectation value is equal to its complex conjugate expectation value, right? For example, let's say you just have I and the complex conjugate of I. I is just equal to I, and the complex conjugate of I is equal to negative I. So here you can see these two clearly are not equal to each other. But if you have the number 2 and the complex conjugate of 2. The complex conjugate of 2 is just 2. So you could see 2 is equal to 2. So if a number is its own complex conjugate, that means it's a real number. If it is an imaginary number, it is not equal to its complex conjugate because complex conjugation takes an imaginary number like this I and slaps on a minus sign in front of it. So a Hermitian operator has expectation values that yield real numbers, right? This is what a Hermitian operator is. And this is important in quantum mechanics because we are interested in looking at expectation values of real things. We don't want to see an imaginary number pop up when we're looking at expectation value of position, because position is a real thing. You're expecting to see the particle here in the real number line. What does an imaginary value for position mean? It doesn't make sense. So we're looking at Hermitian operators. So what am I trying to show here? Is the momentum operator a Hermitian operator? And how do we know, how do we test this? Well, in the book, how a Hermitian operator is defined is this bracket notation, where if the operator is acting on the wave function inside the ket, so here is the ket, here is the wave function inside the ket, the operator is acting on this wave function. And then here we have the bra wave function. So Hermitian operator is one where you can move it to the ket and this thing remains the same. So we want to show, and the reason this line here leads to this line is because here we have the operator acting on this guy. So it literally gives us the expectation value of that operator. You could switch Q and P. And then if you move it onto this side, over here it is acting on the bra, which is the complex conjugate version of this. So this thing will be the expectation value complex conjugate of the operator inside there. So if this is true, then this is true, and then that means this operator in here is a Hermitian operator. Does that make sense? So we're going to check how this works, prove it. First thing I want to write is the operator for momentum, which I'm kind of blanking on right now. I think it is minus I h bar. And then here we have partial derivative with respect to position. Okay, nice. So let's apply that in here. Let's just take this first thing. We have minus I h bar x. And then here we have a psi. Actually, let me pull the psi outside of these brackets. So what can we do with this? Basically, what we want to show is if we manipulate this, we can end up with a version where this moves to the other side. And what we have is this setup where the operator is here. Sorry, the operator is here. It's acting on this. We have this. Can we move this here? How do we do that? Well, let's bring into play the expanded definition of this thing. So what we have here is integral. Then here we have I h bar partial x dx. Nice. These things are identical. We're just expanding it in integral form because it's a bit more comfortable using integrals. We're still kind of fresh and new to Dirac notation. So what can we do here? Well, we could move this outside because it is just a constant. Yeah, let's do that. Minus I h bar psi star partial x psi dx. Now what do we do? Okay, here's what's happening here. I'm going to rewrite this in a more suggestive manner. Partial psi. What we have here is two things. We have a function, and then we have a derivative of a function, and all of these things are inside this integral. What we can try here is integration by parts, because I know integration by parts takes the derivative of one thing and the integral of the other thing. So how I remember integration by parts is this thing is equal to uv minus integral of v du. Now the question is, what is u and what is v and what is du? So we have u here and we have to calculate du, and we have dv. This thing has a dx attached to it, and then when we integrate that we get the v. Okay, so what we want to integrate is the thing with the derivative, because integration cancels out differentiation. So I'm going to put this thing here inside the dv. So I'm going to have partial x, and basically what I've taken is this entire thing and I've called that dv. Then I can integrate, and when I integrate, this thing literally just becomes psi, because I'm integrating with respect to dx. It just cancels out the partial derivative, or the full derivative in this case, since anyway, we're gonna chill with that. So that means the only thing that's left is for this thing to be the u. And if this is u, then du, this becomes partial psi star partial x. Okay. Now let's take this over here and continue that using these little things that we wrote with integration by parts. Okay, so we have minus I h bar. This entire integral becomes uv. This is evaluated at the bounds, negative infinity to positive infinity, because this integral is always from negative infinity to positive infinity. All right? Remember, you have to integrate over all of space. And then we have minus integral of v, which is psi, du, which is partial this, dx. Now we have this closed off. Now keep in mind, this thing, evaluated at infinity and negative infinity, these things have to be normalizable, so they have to go to 0 at infinity. They have to look something like this, like there's some stuff happening here, this is the wave function, but then eventually they have to be 0, because if in the future they explode like that, then this area is not normalizable. You can't find the area under this curve and the square, absolute value squared of this area equals 1. You can't do that, so this entire thing has to go to 0. I hope that makes sense. That's an important thing that you pretty much always use in quantum mechanics, because the wave function has to be normalizable. So at infinity, it goes to 0, 100%. All right, let's simplify this one more time. Let's use this white color here. Minus I h bar. What we're left with is a minus, so this turns this into a plus integral. And I'm going to rewrite, ooh, hold up, I forgot a psi star over here, because this is integral of v du. This is v, this is du. Alright, now what we have here, I can rewrite it a little bit so I can have the psi star here. And we have this, and then we have the psi here. It's okay to interchange these. Nothing is going to happen. It's just multiplication. And these two things are commutative, I believe. Okay, so what do we have here? Let's bring the I h bar back in the middle, back inside here. I h bar partial x of psi star, and then here we have psi dx. This is super close to what we're looking for. What we're looking for is the momentum operator acting on psi star and then this psi. But the momentum operator, as you guys saw in the beginning, is minus I h bar partial x. So we started with this over here acting on this side, right? You can see minus I h bar partial x. We had it here, we used integration by parts, and in integration by parts we were able to move the partial derivative onto the psi star and remove it from the psi, which is fantastic. So you can see here it is acting on the psi star, which is exactly what we want, but we want a minus sign over here. But this is the important thing. This complex conjugate is only acting on this psi. So if we take the complex conjugate to be acting on this entire thing, then this I will get a minus sign. You see what I'm saying? So we will get, boom, minus I h bar partial x psi star and then dx. And this is exactly equal to minus I h bar partial x psi, put the bracket here, and then this. So basically what we showed is that we have the momentum operator first acting on the ket, and then we were able to move it without doing anything, just integration by parts. It's like literally algebra and a bit of calculus, and we were able to move that onto the bra side. So we were able basically to show this. And since this is the case, then you can say that expectation value of P is equal to complex conjugate of expectation value of P. And this is proving that the momentum operator is Hermitian. Thank you guys for watching. Happy Halloween. Try this problem out on your own and see if it makes sense. Then try out and test if the position operator X is Hermitian. We just checked if the momentum operator is Hermitian, and then check if the Hamiltonian operator is Hermitian. The Hamiltonian operator is split up into T, which is kinetic energy, which is momentum squared over 2m. Just replace this momentum with the momentum operator, which is minus I h bar partial x. But also it is split up into the potential energy operator. And here you have many potential energies. So you have the infinite square well, you have the harmonic oscillator, you have the free particle where this is just 0. So it's basically just checking if this is Hermitian. You have the Dirac delta function barrier, the Dirac delta function well, you have the finite square well, and you have the finite square barrier. So you have all of these different potential energy operators to test out, and you can test out the kinetic energy operator, and if you combine those two you can test out the Hamiltonian operator and see if all of those are Hermitian. They should be Hermitian because these things yield real expectation values, I think, but I'm not sure. I haven't tested this out, so we could be surprised. This is quantum mechanics. Anyway, enjoy. Happy Halloween. I'll see you guys later.